So this is the 2017 AP Physics 1, number 3. This is one of the questions that they say is a good model for what the test is going to look like. And if we look at this, there's a lot of words. Yes, they're going to ask you to write a lot and look at a lot of things without manipulating equations, without deriving an expression. Whatever, but fine. We'll play by their rules. Now, if you want to derive an expression and use that to aid your thinking, go for it. There's nothing wrong with that. It just is not going to count for credit in terms of why it meets the obligation. But if that helps you think through it, then that's fine. So what I've got here is I've got a stick. Oh, it's a top view. That's important. So a disc is going to slide along and hit on this stick. That's the center of mass of the stick. And it is pivoted here at the end. Okay. Length D, rotational inertia I. Because this is the Physics 1 exam, they wouldn't have had that. By the way, I of a stick about its end is 1/3 ml squared. Not that we need that. Okay. The rod's initially motionless, free to rotate about the pivot, mass disk, m disk, velocity v naught, perpendicular to the rod. Oh, and it will stick. There's the critical phrase, because I needed to know if it was sticking or bouncing. We're dealing with elastic or inelastic sort of things. We want the rod to end up with as much angular speed as possible, right? Like we want that thing to go. Okay, so suppose the rod is much more massive than the disk, right? So m of the rod is much greater than m of the disk. To give the rod as much angular speed as possible, should the student make the hit? Okay, great. So where do you want it to hit? Well, this is a conservation of angular momentum equation, right? So I would say A, because L equals I omega. I'm not manipulating equations. I'm using them in order to say something, right? And we want omega final to be as great as possible. We need L initial to be maximized, okay? And we would say angular momentum is conserved. Actually, we'll say delta L is equal to 0 because the net external torque here is equal to 0. Therefore, angular momentum is conserved. Okay, great. So then Li is equal to Lf. We know Lf is I omega, right? Here, Li would be of the form mvr. Therefore, to max Li, max r. And that's why we want it to the right. Therefore, to the right of C. See how I'm using equations, but I'm not manipulating them, right? I'm using them to talk about the relationships involved. Okay, on the internet, well, that's dumb. A student finds the following equation, and this. Regardless of whether this equation is correct, what? Does it agree with your quantitative reasoning? That's just stupid. Like, literally, that is just stupid. And the answer is, yes, it does. First of all, don't go looking on the internet. Just derive it yourself. That's just so stupid, right? Omega final is directly proportional to x, right? There we go. We said larger x equals larger omega, so conforms. I'm just symbolically doing as much as possible to make the grader's life easier. Okay. Now, if I could type these things, I'd probably end up typing them because I could type a lot quicker than I write. C. Another student deriving the equation makes a mistake and comes up with this. Oh, so once again, got something wrong off the internet. Without deriving the correct equation, why not? It's stupid. How can you tell that's not plausible? Oh, okay. Got it. Now, the first thing I actually thought of doing here is checking to see if the units check out, because if the units don't check out, your equation is not plausible, right? I need radians per second on the right. I is in kilogram meters squared. X is in meters. Velocity is in meters per second divided by kilograms. Oh, okay. So they were intelligent enough to make sure that the units would cancel out and work. So that's not what it is, but that's always a good one. See if the units work out. Oh, so the problem here is with dependencies. There it is. Okay, right? If I is larger, this equation says omega is larger, right? Because they're both in a numerator here. It's like, but I is rotational inertia. So they really want you to talk about rotational inertia, right? A larger I would mean less change in motion for bar, and you expect a lower omega. Great. Done. Awesome. Oh, there's more. Delightful. Okay. For parts D and E, do not assume that the rod is much more massive than the disk. Okay. We won't assume anything. Immediately before colliding the rod, the disk rotational inertia about the pivot is that. Okay, so that's just mr squared, so mx squared. And its angular momentum is that. Derive an equation. Oh, this is silly. Okay. All right, so Li is equal to Lf. Right, the net external torque is equal to 0. They tell us that this is m disk v naught x, which we already knew. And then finally, what do we have? Well, we're looking for deriving expression for angular speed. So I'm looking for I cis omega, right? So I cis here is equal to I rod plus m disk x squared. And I rod is just I. So that's what our answer is. Omega is equal to m disk v naught x over I rod, or I don't have to say I rod because it's just I, that's the term, plus m disk x squared. Boom, that's actually what it is, right? Because the system is now this with the object stuck to it. And so that's D. E. Drive now, the disk bounces back. Okay. Is the post-collision angular speed greater than, less than, or equal to the post-collision angular speed of the rod when it sticks to it? Okay, explain your reasoning. All right, so what is happening here? So it bounces off. Okay, so we can say, oh, okay, so if I've got this and it sticks versus this and it bounces off, in which case does this object, the rod, receive the greatest impulse? It is in this one. So we're going to expect this thing to actually be moving faster, believe it or not. Because at first I was thinking, oh, okay, well, here all of this energy is going into this thing, but only some of it's going into this thing. But the problem here is that this is an inelastic collision, so there's a loss in energy. But here, there's no loss in energy, so even though this thing still has energy finally, it can impart more of that to this and still have motion afterwards. I think the answer here is about impulse, right? So the answer is greater than, because the rod receives a greater impulse when bounce off, right? Because the impulse here, going to be delta L would be the impulse, would actually be if we say this direction is positive, like an M negative V R minus M positive V R, so that you end up with actually a negative 2 MVR is the impulse on the ball. Therefore, the impulse on this thing is also 2 MVR. It's a larger impulse, so greater than.